Let's start today's class. Also check your attendance on the blackboard. Okay, do not forget check your attendance. Okay, then also did you enjoy long holidays? No response. Okay. So I believe everyone had the long holiday, it's almost 1 week. Okay. Okay, so what did we learn before holidays? So we are learning about the RISC-V instruction. So which means this is the instruction set architecture. So it's designed for computer processor. So actually, the instruction set architecture is designed and computer hardware is designed based on the instruction set architecture. So you can understand that ISA, instruction set architecture, is just a promise or protocol or rule for designing processor, right? And then we are learning about the RISC-V, okay? And then we learned about the arithmetic instruction, the previous class, right? Then I believe you can easily understand about the format of the arithmetic operations, right? It's very similar to our real arithmetic operator, right? Like the plus, minus, and multiply and divide. So, and then also I explained that these instructions require operands, right? So data are read from operands, and then the result, the result of operation is stored to the also operand. Okay. So in a computer processor, actually in the previous class we learned about the two different operands, registers and immediate. Okay. So it's very important. Okay. So what are registers? It's the small memory space. Then this memory space is very fast. Okay, because smaller is faster in the hardware, right? Also in the computer system, smaller is faster. So usually the operations such as the arithmetic operation or the normal operations require a fast processing, right? Because it is related to the performance of a computer system. So now to perform operation quickly, then we can store the required operand data in registers. Okay. So RISC-V. So actually the size of a single register, so it's called a width of a register entry. And then the number of registers is defined in ISA manual, right? In the RISC-V, the RISC-V processor has 32 integer registers, so it is also called the general purpose registers. Okay, and then the size of size of a register of I32I is 32 bit. Okay, because it's a 32-bit computer. Okay, so which means that the width of a single register is 32 bit. Okay, then also we can use the ABI name instead of register numbers. Okay, because each register can be used for different purposes. Okay, and then actually we can use this register instead of register numbers. But if we use the key 0, then it represents the X5. Okay, so actually this register number is used for encoding machine instructions, right? We'll, we'll learn about how to encode machine instructions later. And then, so normal instructions, like the normal arithmetic instructions, use register operands. Okay, and some instructions can use immediate value. So immediate value is a small sized constant. Okay, and then for the immediate value, we use signed numbers. Okay, so actually the RISC-V instruction we use three different operands: registers, immediates, and memory. Okay, so and then in the previous class I briefly explained about some basic memory instructions. Actually, there are two kinds of memory instructions: load and store. Then actually these two kinds of memory instructions are distinguished by direction of data transfer. So what is load? So what is the definition of load instruction? The data is read from memory, okay? Read from memory, and then the data is transferred to the register. So this is the load instruction, okay? And then the opposite direction is performed by store instruction. Store instruction reads data from a register, and then this read data is stored into memory. Okay? So actually the direction is just opposite between the load and store instructions. Okay. And then actually the RISC-V is this is the RISC type instruction. Okay. And then also in the RISC-V, only store load instructions and store instructions can access memory. Okay. So for example, add instruction. So add instruction just handle register operands and immediate operands, but the memory is not used by arithmetic instructions like add. So these memory instructions are just to handle the memory data. The memory data are just handled by memory instructions, load and store instructions. So for the RISC type instructions, only memory instructions access memory data. Okay, but CISC is different. So some arithmetic instructions can directly access memory data for the CISC type instructions. But for the RISC type instructions, the memory instruction right? Only memory instructions can access memory data. Okay. Okay. So operand is memory, and then actually we just store every data in memory space. Okay. And then also the memory space is very large. Okay? Usually, physically, and then modern computer systems employ very large memory recently. So it's larger than 4 GB. Also, for 32-bit computers, the maximum size of memory space is also 4 GB. So just to compare, so for the registers, I explained that there are 32-bit registers for RISC-V. So actually the size is very small compared to the memory. So actually the maximum size of the memory space is 4 GB for 32-bit computer. So it's very large compared to the registers. So every data actually array structure and dynamic data that I explained. Also, we can access the instructions from memory space. So actually, we can find every data in memory. So it's called the main memory. Okay, and then enough to access. So which means that initially there are no data in registers. Okay, then so required data actually needs to be read read from memory space. Okay, so if we use the compiled code, so I believe everyone is performing lab 1, right? I think the deadline is tomorrow. Okay. So if you see the some code, the dump the instructions from the binary file, you can find the instructions such as load word. Okay, LW is just a load instruction, so this is the load word instruction. So I believe you can frequently observe load word instruction, the first lines of your dump code. Okay, so it is because so when the code is executed first, the data exists in memory space, and then these data need to be transferred to the register file. That's why we can observe many load word instructions in the dump code. Okay. Also, you can find the many store SW means the store word. This is the store instruction. Also, for most computers, memory is byte addressed. So this is very important. You need to understand how the memory address is represented. Okay. So what is the byte address? The memory address 1 is number 1 is assigned to the 1 byte of data size. Okay, so which means that memory address 0x00. So let us assume that 0x00 is also assigned to the 8-bit data. It's a one byte of data. Then the next address 0x01 is pointing the next 1 byte of data. Okay, so for the most computers, memory address is byte address. Okay, so it means that memory address 1 occupies the 1 byte of data space. This is very important. So actually, I don't know. Actually, one student posted the question why the maximum size of the storage to be computer is 4 gigabytes. So we can actually calculate. For the 32-bit computers, the size of address is 32-bit, right? Because actually we can access the memory using the register. The address is stored in the register, and then the register size is 32-bit for the 32-bit computer. So which means that using the 32-bit computers, addresses can be represented with the 32-bit binary format. Okay. So what is the maximum size of the memory that can be represented using 32-bit binary data? Okay. So which means that the size is 2 to 32 byte, right? So it is because the memory address 1 represents the 1 byte of data. Okay, and then there are 32 bits that can represent the address of data. Okay, so which means that we can totally represent 2 to the power of 32 byte, and then this is actually 4 gigabyte. Okay, that's why the maximum size is the 4 gigabyte. Okay. So some students posted the questions on Piazza, and that's very good practice. And then so please answer very kindly, right? So right. So please post your questions on Piazza. Okay, then let's see how to represent how to assign data in the memory space. So actually, so you can find that in this bullet, you can find that RISC-V memory is little endian. What does that mean? Okay, so little endian. So let's see what it means. Okay, so there are two kinds of representation of memory address. Okay, so actually we frequently handle data in memory. So actually we frequently handle multi-byte data. So which means, so if you see the load instruction in your dump code, you can find the actually load word. Okay, so what is word? So we already know that byte is 8-bit. Okay, and then actually the word is the 4-byte. Okay, so which means the 32-bit data. And then actually half word represent the 2-byte. Then double word, obviously 8-byte. Okay, so word actually represent the 4-byte of data. Then, which means that if we execute the load word instruction, then we need to decide how the data. So load word just handle the 32-bit data, and then we need to decide how this data is allocated to the memory space, because this is 4-byte. Okay. So this is the 4-byte. So which means that we need to store this 4-byte data into the memory space. But the memory space is the byte address. Okay, byte address, which means that each memory address 1 represents the 1 byte of data. So there are two different allocation methods in the computer system. So it's a little endian, okay, and big endian. So actually the RISC-V employs little endian system. Okay, so what is a little endian? So if we see that this 32-bit integer data, then the LSB is the bin number 0, and then MSB is the bin number 31. And then if we divide this data into byte, then this is the first byte, this is the second byte, third and fourth byte of data. So little endian means that this data, this 1 byte of data is assigned to the minimum, the smallest address of this memory space. So this is the little endian. So if we just set the byte number to this data, and this is the byte number 0, so 1, 2, 3. So in the little endian system, the byte number 0 is assigned to this smallest address space. Okay, and then byte number 1 is assigned to the next address space, a plus 1, 2, a plus 2, and 3, a plus 3. So this is the little endian system. Okay, so which means that if we just execute some load word instruction, like so load word some data, this data, and address 0x1000. Okay, so this is the hexadecimal number 1000. Then the first byte of this data is stored in the address of 0x1000, and then the next byte number. So this is the next byte. So this is stored in the 0x1001. Okay, and something like this. So this is the reader endian system. A big endian is opposite. Okay, so this is storing to bit data, as you can see. So this is byte number 0, 1, 2, 3. So with the big endian system, the byte number 3 is stored in the memory space that is mapped to the smallest address. Okay, so this is the big endian system. And then actually the RISC-V uses the reader endian system. Okay, and then I believe the reader endian system is more not intuitive, but it's more obvious to the computer addressing. Okay? But you can you need to distinguish two different endian systems, little endian or big endian. Okay, sometimes some processors may support the big endian address system. Okay, this five is the little endian. So let's see how the byte address is assigned. Okay, so actually I already explained, but I will explain in this slide. Okay, so we use the byte address, right? But we frequently use the word-based memory instructions like load word or store word. So actually, so if you are familiar with the C, the size of integer is also 4 bytes. Okay? Usually 4 bytes. So this is actually word size. So that's why we frequently use the load word or store word instead of load byte or store byte. Okay? We frequently use word size memory instructions. So then, so this is the address of the memory, and then actually, but the RISC-V use the byte address. So which means that if we just access address number 0x0000 like this, then it represents the memory address 0, 1, 2, 3. So memory address 3210. So this is the memory space accessed by this load word. Okay, and then if the address is 4, then address 7654 is the accessed by this load word instruction with the address 4, 0x04. Okay, so you need to understand how the word address will map this byte address. So if we use the load word or store word instruction, then you need to understand how this data, this instruction access the byte address memory space. So this is the example. So this is load instruction and then load a word. So this is actually load word, then load a word data at memory address A. And then, so which means that this is the load word and then it accesses the memory address 0x08 and then read the data from the memory address 0x08 and then this data is transferred to this register, destination register S3. So this is the example. The example code. So it's a load word instruction, and then this is the destination register. So for the load word instruction, the destination of part is register. So as I explained, the load instruction reads data from memory, and then this data is transferred to the register, right? So which means that the destination of column of is load instruction is register, right? And then, so if you see the is here, you can find that oh, this is A and then this is 0. So 0 means actually x0. So register number 0, but it is equivalent to 0, right? So actually when the load word instruction is executed and load word calculate the address of memory in this part. Okay. So if you see this part, you can find the register here is the source register, and then you can find the offset. So actually this is the also immediate data. So using the data in the register and immediate value, then load word calculate the address, the target address. So in this example, oops. So in this example, the data in 0 is 0, right? So 0. And then the immediate value is is 8. So which means the target address becomes the 0 plus 8 equal 8. So this is the target address of load instruction. Okay. So load word instruction access data in this address. So it's address 8, and then read the data, and then this data is transferred to the destination register. So if we see check the word address 0x08, and then I already explained that this is the load word, and then which means that this load word reads data from address 8, 9, A, B. Okay, it's hexadecimal. And then as you can see, so this is the data. Okay, so as you can find that the data is 01 at BE2842. Okay, so this is data. So this amount of data is read from the memory, and then this data is stored in the S3 register. This is how the load word works. Okay. And how about the store? So as I explained, the data direction. The data direction is opposite to the load instruction or the store instruction. So example is that store the value held in T7. So which means that this is the source register of the store instruction, and then it is stored in the memory address 0x10. And then this is the example code. Okay. Actually, if you see the RISC-V instruction, the store word instruction, the instruction format is actually the same to the load instruction, right? So you can find the register here, and so you can find another register here, and then offset here. But as I mentioned, the direction is opposite. So which means this is a source register. Okay, this is the source register for the store instruction. Okay, so let's see the behavior of this store instruction. So firstly, we can generate the address from this part, and then so it's the same. Actually, the same rule can be applied. So 0 has the value 0, and then offset is 0x10, So 0x 1 0. So that means that the target address is 0x 1 0. So this is the target address of the store instruction. And then store instruction read data from the T7. Okay. So let us assume that T7 has the data A, A, B, B, C, C, D, D. Okay. So then store instruction read this data from register T7, and then so address is 1 0, right? And then I already explained that this is the store word, so word instruction. So which means it will access the 1 0 1 1 1 2 1 3. Okay, because you need to access the 4 bytes of data. So after reading this data from the T7, AA, BB, CC, ED is stored in the memory like this. So you can find that this is RISC-V uses the mirror endian system. So ED is here. This is the byte number 0. So ED is stored in the address 1 0. And then the next byte is CC. So CC is stored in the byte address 11. Okay, understand? So this is the behavior of store instruction. It's a store word. Okay, so let's see another example. So this is the C code. So and then you can find that. So this is the array data. So A12, and then A12 is H plus A. So in this example, you can find the it's an array, right? It's an array data. So array means that so array data includes the multiple elements, and then the size of these elements are the same. Okay, and then so this is the integer type data, and then if you see that this command, then you can find that H in X21. So I do not use the ABI name. I just use the register number here. And then base address. So what does that mean? Base address of array A is in X22. What is the base address? So if you see that this array, so you can, so this is the array A, and then which means that the array A is the multiple elements such as A0, A1, A2, and then A1. Okay. So A has multiple elements, and then base address represents the address of the first element A0. Okay. So which means that the base address of A. So it means it is on address of A0. So which is the X22. So, but you can find that in order to perform this operation, then we need to access the A8. Then how can we calculate the address of A8? So we know the base address, the address of A0. And then, so I mentioned that this is the integer data, so which means that the size of a single element is 4 bytes. It's 4 bytes per word. Then how can we calculate the A8, the address of A8? So actually, the array data is allocated to the memory space regularly. So which means that, so this is the base address of array A. Then the next element, A1. The address of A1 is actually its base plus 4. Why 4? Because the size of this single element is 4 byte. Okay. And how about the A2? This is the base address plus 8. So 4 multiplied by 2E. Then how can we calculate the A? A is the base plus 4 multiplied by 8. Okay, we can calculate the address of A like this. So if we see that this load word instruction, so you can find, so I mentioned that the base address is stored in the X22, okay? And then you can find that this is the offset. So you can find this is 32. So which means that in main base address plus 32, right? Which means this load word read data from A8. So let us assume that this array data is in memory. So load word reads data from A8, the memory space of A8, and then this data is stored in the X9. Okay, and then so H is in X21, so it performs the add instruction. So it's H plus A. So it is stored in the also X9. Okay, so this value is stored in the X9 by this add instruction. Then we need to store the region to the A12. So we can calculate the address of A12 in the same way. Okay, so 12 equals to 12, so which means that each base plus 12 multiplied by 4. Okay, so it offsets the 48. This is the base address, and then the result is already stored in the X9. So using the store word instruction, read data from X9, then store this data to the address of 48 plus base address. So this is the example of RISC-V assembly code. And then I hope you can understand the behavior of load word and store word instruction using this example. So okay, so I will show some example of the example sequence because so in this course I will frequently use the operator and so actually if we use the operator and in front of variable name, and then actually it represents the address of variable A. Okay. So actually if you run C programming language, then I already learned about the pointer, right? So actually we use this AND operator for representing address. Then actually the pointer is the kind of address. So it's actually a little bit different, but the meaning of pointer is just the address of this data space, the address of variable. Okay, so slightly different, but we can understand that. Oh, if we just declare pointer, then which means that we are handling addresses, and we can represent the address of variable using this AND operator. Okay, the AND A. So actually in this course I will frequently use this operator. That's why I just showed this example. Okay. So if we study this example, this is the integer type print a. So if we just use the printf function, then we can just display the value of a like this. Okay. But if we just use an a, then we can just display the address of variable a. It's the same to the array representation. Okay, so if this is the array B, then we have the 4 elements. Then if you want to see the data of is P, then we can just directly use the variable P and the element name. But if we just add the end operator in front of this variable name B, then it represents the address of P I. Okay. So actually, I mentioned that the C is a kind of the low level language. So that's why he has a pointer. Okay, so which means using a pointer, then we can just handle the address of variable. Okay, and then in Python there is no concept of a pointer, so address. So Python just handles the data, not address. But so actually, the program, so we can just handle the many addresses. Okay, so like so addresses are just stored in the register file, and if we give this data, then we can just calculate the address. So actually, computer system, we frequently the programs frequently handle addresses. And then using C, we can directly handle addresses using a pointer. Okay, so that's why I showed these examples. Okay, so I summarize the registers and memory data. So immediate is the constant data, and then this immediate data is included in the instruction. Okay, so but we computer systems we use the two storage space or memory space. Actually, we can say that the computer systems use two storage spaces. Okay, which means data is stored. Data can be stored in the registers and memory. Okay, so also the start of this chapter, I explained that so I hope you remember this figure. So instructions are executed, and I mentioned that instructions change state of hardware, state of processor, but this state represents the architectural state, and then I mentioned that architectural states represent the data in register file and data in main memory. So which means that actually these instructions just handle data in register files and main memory, two storage spaces. Okay, but actually in hardware there are many memory components like the cache. We will learn about the cache later. Actually, there are many physical memory components. But for the software just handles these two kinds of storage space, like the registers and memory. It is because actually when the instructions are defined in the ISA manual, and then these instructions just handle data in registers and data in memory. Okay? So you can understand that when an instruction is executed, then you can understand that, or you can understand like the data. the data is changed, but data in register file or data in memory space. Okay, that's it. That is the data defined by software. Okay, by software. But hardware is different. The hardware has many memory components. Okay, so because we need to execute instructions more efficiently and more quickly. So that's why the hardware is very, very complex. But when the software is defined, software just handle the computer systems that software just change the data in registers and memory, and that's okay. Okay, so which means that we can just compare the two different data spaces, like the registers and memory. And as I mentioned, registers are super fast. Okay, is it because the registers are extremely small? The register file is extremely small, so it means the registers are very, very fast. Okay, much faster than the memory. Okay, but we can store more data in large memory. Okay, so compiler. So you are doing the lab assignment number one. So when a high-level language code is compiled, actually the compiler uses the registers to store temporary data. But I mentioned that the number of registers is limited, so it's just 32 for RISC-V. So which means that the registers are actually very precious resources. Okay, because there are only small number of registers, but it's very fast. So which means that compiler needs to registers efficiently. Okay, register optimization is important. Okay, so you can just compare the registers and memory, and then so this is the summary of the memory instructions. So I mentioned that there are two kinds of load and two kinds of memory instructions, load and store. Then we can classify load instructions by size of data handled by load instructions. Okay, so as I mentioned, if we can frequently find load word from the normal code because the data size is usually word. Okay? But we can use the different kinds of load instruction, like the LB, which represents the load byte. So it means that just a byte data is read from the memory, and then this byte data is stored in the register byte. So this is the load byte. So we can find the load half word. Half word is 2 bytes of data, and then load word. And then we can find some different instruction like the LBU and the LHU. The load byte unsigned and load half word, load half unsigned. So I will explain later about this unsigned load instruction. But we can understand that there are many different different kinds of load instructions by the size of data handled by load instruction. And store is the same. Store has the store byte, store half word, and store word instructions. Okay. Okay. And then I will briefly so I actually enough to explain the LBU and the LHU. Okay. I first need to explain about the signed and unsigned numbers. And then if you took the logic design course, and then you already know about the signed and unsigned number. I think that actually this is the basic of the binary number system. Okay, so if we use the unsigned binary integer, then which means that each digit represents the plus number, right? So actually each digit represents the power of 2, and then the digit number represents the sign of is power of 2. Okay, so but the binary number system, actually we have only two kinds of number, or 0 and 1. So which means that for the number is 1 for a certain digit, then we can just add the 2 to the power of n. For the n is the digit number. Okay. So what is the unsigned? Unsigned means that so we can just calculate the magnitude of number. Okay, not the sign is not constant, but we can represent the negative number using the 2's complement signed number system. 2's complement number system. So the 2's complement number, the MSB, only the MSB represents the minus number. So which means that if we just check the MSB, so it's for the world data, the MSB represents the pin number 31. Okay. So if we just check the MSB, the most significant bit, then if the MSB is 1, so which means that it's the negative number. Okay. And then if the MSB is 1, then which means it means the minus, this is the digit, and then digit multiplied by 2 to the power of n minus 1. Okay, so this is the 2's complement number, right? And then as I mentioned, we can check the MSB to check the sign of this 2's complement number. Okay, so why is it important? Because so there are two kinds of load instruction, LB and then LBU. And then you can find that LB is the byte load, which means that the byte data is read from the memory, right? So this is the byte address here. And then this is the byte of data, like the 11110000. And then with the load byte instruction, this data is read from the memory, and then it is stored in the register file. But the register file size is 32 bit. So what's the problem? If we just perform this load byte instruction, then this load byte instruction can fill only the part of register file, only this amount of data, the first 8-bit data. And how about this space? So if we use the just LB, then it means that the processor assume that this data is the signed number. Okay, so it's a signed number. So which means that we check the MSB of this data. Okay, so in this example, the MSB is 1. So which means this is the negative number. So we just perform the LB, then we need to fill this register file using 32-bit data, which means the 32-bit number. Okay, so in this case, the MSB is just repeated. Okay, so this is called a sign extension. Okay, so we just read the 8-bit data, but this 8-bit data is stored in the large space, so like the 32-bit data. So which means that we need to fill the remaining part of this space. So, and then if we apply sign extension, then we check the MSB of the source data, and then this MSB is just repeated. This is called a sign extension. But if we use the LBU, then it means LBU think that, oh, this data is the unsigned data. Okay? So which means the MSB is just a magnitude of this number. Okay, that's sign. So which means if we just use the LBU for this data, then zero extension is applied, which means not one. Zero is filled in the remaining space of the register file. So it is because there are two different kinds of LB or LH instructions. And then if we just use the normal LB or normal LH, then it applies the sign extension for this register space. Or if we use the LBU or LHU, then zero extension is applied. Okay? Actually, we need to also classify signed number and unsigned number in the code. So if you use the C, like if we use the data type like the integer, so instead actually this is the signed integer, right? But if we just declare the variable which is the unsigned int, then instead of this data is the unsigned number. So the meaning is different. And then actually we also need in the computer hardware also handle the signed number and unsigned number with a different approach. Okay, so it is actually important because if we just apply some incorrect signed or unsigned approaches, then computers will generate the incorrect result. Okay, so we need to avoid this case. So that's why C has some unsigned integer and integer. Okay. And so and then I just added this slide to explain about the different instruction like LB and LBU. Okay. So you need to just understand how the signed and unsigned numbers are represented, and then how the computer hardware like these five processors handle these different numbers using different approaches. Okay, so then let's see some different instructions and generating constant. So actually the RISC-V also supports some instructions for handling constant data. So it is because in our code, we frequently use constant numbers. As I mentioned, we frequently use the A equals A plus 1. So this is the constant number, right? So then I also explain why instructions support the constant numbers, like the immediate numbers. So this is because enough read data from this memory. The memory is very, very slow. So then if we want this data is just one. If we want read this data from the memory, then it will take a long time. Then take a long time, it means performance will be very low. Okay? We need to avoid this situation. So actually the RISC-V provides some instructions that can handle constant numbers. Okay, so this is the example. So firstly, we can generate the 12-bit constant using add I instruction. So this is the 12-bit constant. Okay. So it is because if we use the add I, okay, so add I is the add immediate instruction, and then which means that add I use the one source register like the A0 and then immediate number. And then actually the size of this immediate number is 12-bit signed number. So this is important. So this is because so actually the instructions are encoded into the machine code, and then this machine code is stored in the memory, which means that it's hardware. Okay, so it's a hardware data. And then actually the size of this immediate data is restricted by the number of bits assigned to this immediate field. Okay, it is just 12 bits. So which means that if the size of this signed number, so of course I mentioned that this is the signed number. If the size of this constant number is smaller than the 12-bit signed number, then we can generate this constant number using add I. Okay, the small constant number. So this is the example. So A is minus 372, and then B equal A plus 6. So we want to store A into the store minus 372 into A. And then, so first way is to store this data in the memory and then read this data from the memory. But this is very slow. And then we can, by using add instruction, we can simply store this minus 372 into S0. How? We have 0 register. This is X0, right? This is the X0. So which means that it means the S0 equal 0 minus 372. Actually it's a plus, but it's immediate minus. Immediate number is the minus. So because it's add I, so this means the S0 equal 0 plus and then minus 372. So because this value is already 0, then we can generate the small constant number easily. Okay. And then for this, the next instruction B equal A plus 6, also we can implement this statement using one line of RISC-V instruction and I. So for the 12-bit constant, then we can easily generate this 12-bit constant number using add I. Then how about the large constant? Can also, so this is the example. Int A equal, this is the large number. So it's hexadecimal format. So actually this number size is 32-bit. So in order to support this large constant number, the RISC-V also provides the instruction LUI. It means the load upper immediate. So that's why it's called the LUI, the load upper immediate. So actually the behavior of this LUI is this immediate number. It's the 12-bit immediate number. 12-bit immediate number into the upper part of the register. So register size is the 32-bit, so from 31 to 0. And then, but actually the LUI can handle the 12-bit immediate number. So, and then LUI, this is the S0, LUI put this value into the upper 20, so which means 31 to 2, right? no, 12, 12. Okay. So this data is stored in the upper part of the S0. The first 20 upper part of the register, and then you can just store until you can just store until this amount of number. How about the remaining part? We can use the add I. Right. So if you see the next instruction, we can find the add I S0, S0, and then 0x 7, 65. So this number is here. So if we want for large constant number, then we can first store the first 20 bit using LUI instruction. Then after that, we can use the add I instruction. Okay? But you need to remember that add I just handle the signed number. Okay? So what does that mean? So which means that if add I performs the add operation and plus, then this 12-bit immediate number is extended to the 32-bit using sign extension. Okay, so here, so let's see the example. So we want to store this data. So what is different? So firstly, we just store this data to the S0, right? And then, so in order to store this data, the 32-bit data, we first store the upper 20-bit here, and then this is the lower 12-bit. So which means it is the 0, 1, 1, 1, 0, 1, 1, 0, 0, 1, 0, 1. So actually, it's the 12-bit immediate number, and then MSB is 0. Okay? And I mentioned that the add I use signed 12-bit immediate number. Okay? And then fortunately this is 0, so which means that it's the plus number. So that's why we can directly use the 765 in the next instruction. But in this example, so this is a little bit different. So if we see this part, so this part, okay. Then what is the EAB? EAB is the 1, 1, 1, 0, 1, 0, 1, 0, 1, 0, 1, 1, right? So what is different? MSB. MSB is 1. So which means when the add I is executed by a processor, then add I think that, oh, this is the minus number, negative number. So it just extends the 1, 1, 1, 1 for operation. What's the problem? In this case, so using the LUI, we just store the upper 20-bit here, and then actually this is 0, 0, 0, 0, and then plus 1, 1, 1, 1, 1, 1, 1, 1, and EAB is executed by a processor. The problem is a certain number plus 1, 1, 1, 1, 1, 1, 1. This is the different number. Right? You understand? So the previous example, the MSB is 0, and then the sign is extended. Then actually the 0 is repeated because the sign is 0. So actually in the previous example, upper 20 bit is here, and then 0, 0, 0, 0, and then next 7, 6, 5, and then 0, 0, 0, 0, 0, 0. And then it's added. So which means, oh, this is same because the all 0. The all 0, then it's a 765. Okay, so no problem. So we can just we can easily create this large number using LUI and I. But in this example, the problem is, EAB is the MSB is 1, and then the add I is executed, then this EAB is extended to the 32-bit using sign extension, which means this data is 1, 1, 1, 1, 1, 1, 1. And then it will generate some different number. EAB is the same. So in this case, so we need to consider this situation. Okay, so which means actually, if you see this LUI instruction, then actually the original number is the FEGCA, but you can find that this is the FEGC9. Right? So it is because we already know that EAB is the minus number. Okay, so when the add I is executed, then 1, 1, 1, 1, 1, 1 will be added. Okay, so actually this is the inverse complement number. It's -1. Okay, so that's why the 8 is changed to the 9. So we already know that this is the minus number. Actually, it's not. But as I think that this number is the minus number, so which means that 1, 1, 1, 1, 1, 1 will be added. And it will be added. So which means actually the -1 will be added in the upper 20-bit data. So which means we just add the number 1 to this data, and then after that the -1 is performed by add instruction. So you need to understand that the add I sign extends its 12-bit immediate. Okay? Actually, if we use the 12-bit immediate, then it's the signed number. It's the same. Also, the load word and the store word also use the 12-bit immediate number. But we need to remember that this immediate number is the signed number. So we need to consider the signed number for generating RISC-V assembly instruction. Okay. Okay, so I need to stop here. Then okay, so I stop here. Then see you again. Thank you for listening. Okay, I'm done.